Hello, everyone. Welcome back. Welcome to the next session of Particle Physics for Teachers. I'm really excited tonight to introduce you to my friend Federico. I met Federico at the Science on Stage Festival in Prague. He was on Team Italy, representing Italy, and I was on Team France. And he pulled me aside and started telling me about his science picnic, showing some of his experiments. And I think he said, if I'm ever in Brescia, let him know. At any rate, that's what I did. And so when I was in the area this summer, I asked him if he'd like to meet me, and he welcomed me to his home, showed me tons of his experiments, including some that were inspired by stuff I've done. So it was absolutely amazing to see that. One of them was this homemade drift tube. So I've been meaning to make one of my own. I still haven't gotten around to it yet. But I talked to people back at CERN like the week after I was with Federico, and they said they're interested in learning more about it too. So I can't wait to see him actually put it together and to have this shared with all of you guys. So without further ado, thank you again for joining us, Federico. It's a pleasure to welcome you and turn things over to you.
Thank you very much, Michael. I'm very happy to be here. Thank you for inviting me. And I'm not alone here, actually. Then here with me, there is my friend and colleague, Stefano, and two of my students that will develop the project in the coming months. So they will help me showing you all my stuff and broadcasting this recording. I would like to organize this session in 3 steps. In the first one, I will show you some pictures, a slide presentation about the whole project, just to get an idea about what we are talking about. Then in the second step, we are going to use the ionization chamber to measure some radioactive particles. And we also go and get some samples of radon daughters here in the basement of my school. And in the third stage, we will share some ideas and activities with the ion chamber that we are going to study today. So first of all, I'm going to share my screen and go to this website. Okay. So first of all, I am a physics teacher, but I'm also a leader of a scientific association called Aghi Magnetici. And my presentation, my slide presentation is available on the web, and I will show you how to get it. So Aghi Magnetici, meaning magnetic needles, but Michael put this link to the website on the schedule of Part Physical for Teachers. So anyway, this is the website, and here it's in Italian, okay, but there is also a menu in English International Project. And here you can see the last project is Radon detector experiment. So it's available and you can check whenever you want. So let's start with the presentation. And first of all, yes, I'm a physics teacher in the secondary school, and I teach physics with the teenagers from 14 years of age to 18. Just a few pictures about my activity as a science communicator. I developed STEM project within the primary school and also in the secondary school. Here you can see me with the CERN helmet during a public event here in my city, Brescia. You can see with the sunglasses my students that are very confident with physics because they are helping me to promote some science stuff. And I also promote some event and conference for adults. For example, here I am with one of my students, and we are tuning a homemade radio. And I'm also active with children at an international level. Here I am in England, promoting some science experience and experiments about water. We really had fun there. And I'm also involved in some speaking, in some session about science and STEM activities with teachers. Here I am in Bulgaria, and here I am in Ukraine. Anyway, let's go on and talk about the ion chamber we are going to study. First of all, the radon gas. Why we are studying the radon gas? But first of all, the radon is everywhere, essentially. We can find generally in our soil, the rock, in the concrete. It's trapped inside, but as a gas, it spontaneously goes up. And once it reaches the air, it is mixed in the air. So actually, I'm breathing now air with radon inside. From a chemical point of view, radon is not harmless. It's not a dangerous gas. I mean, it's a noble gas, so it's hardly bound with other elements. It's chemically inert. But from a nuclear point of view, the situation is very different. This is the chain of the radon decays. You can see that the radon decays in about 4 days, meaning that it's a short time, and in a few days, radon will become polonium, lead, piombo, and bismuth through some particle decays, alpha decays, and beta decays. These particles, alpha and beta, are very energetic and interact easily with matter. So it is not the radon gas dangerous in itself, but the product of the decays really are. So polonium, piombo, bismuth are called the radion daughters, and these isotopes are really dangerous. Why the radion daughters are really dangerous for our health? As radion gas is mixed with air, we usually breathe radion. And once the radium decays in our lung, the radion daughters will emit some particle, essentially alpha particle. And alpha particle is very energetic and could damage the DNA, for example, breaking some chemical interaction between different molecules. So that's the point. And in many countries, the radon is the first or second reasons why a lung cancer take place. So if we are able to measure the radon in a room or in an environment, in a basement, in a building, it will give us some indication about how healthy is that place. Let's talk about the ionization chamber we are going to see. I'm happy that on Tuesday, Jesus gave a brilliant explanation about the detectors, remember? And also the previous speaker talked a lot about detector. So it's not a surprise to see a detector also in this session. And if you remember, on Tuesday, we saw a drift tube, meaning that it was a 6 meters long tube that CMS detector uses at CERN. You can see that the ionization chamber in the picture is just the same. I mean, the principle is the same. We have a tube with a wire inside. The ion chamber is nothing more than the tube with an iron, with a wire inside. On Tuesday, Jesus told us that usually inside these tubes there is a special gas. We are going to use the air as a gas, okay? And when a radioactive particle come in the chamber, many of the molecules are ionized. So some electrons become free. And if I apply a voltage between the wire and the outer can, these electrons can be collected on one of the two poles, meaning that I have a very tiny current. This is the scheme of a project. You can see on the left the ion chamber. And if I apply a voltage, I have a power source, a battery. If I apply this voltage, the electrons will be collected and the tiny current will take place. Of course, this current is really tiny. I mean, femtoampere, meaning that it's about thousands of electrons per second. And we have to measure this tiny current. So we have to ask for a help to the electronics, but it's not that complicated. Just a transistor. Transistor is a small device that amplifies the current. So if I put a transistor in this simple circuit, I can have a current that I can detect with some instruments. So this is the final scheme of a project. You can see a transistor, a special transistor called Darlington, and I will show you later how it looks like, and a digital voltmeter to read the current in the circuit. This final scheme is about the ion chamber that I'm going to show you in a few minutes. You can see on the left side the ion chamber with the wire inside, the digital voltmeter, the power source, the transistor, and at the top, the resistance. Let's have a look directly to the stuff we are going to use. This is the digital multimeter. This is the transistor. There is a resistor. A wire, just a copper wire, of course, bare copper. And okay, here is very, very simple material. And just look about the connection. The wire is connected just inside the can, and this is the connection of the transistor. I'm not giving you detailed instruction about how to prepare this chamber at the moment, but in the reference at the end of my presentation, you can find material on the web with all the detailed instructions so that you can't fail preparing the stuff. So once the ionization chamber is ready, we just have to put a radioactive source in front of the can And the radioactive particle will come into the chamber, will ionize air molecules, and then the electrons will be collected and the tiny current will be read on the multimeter. Of course, we can't read exactly the current because it's too difficult, but we can measure a voltage. This experiment is not about measuring precisely the radion gas inside a room. We cannot do it. But we can measure a proportional quantities, for example, this voltage, and then compare the value with the one measured in other places. So we are going to measure the radion inside my lab, then we are going to measure the radion gas in the basement, then we are going to measure the radion gas in another room, and then we will compare all these data and try to understand what's going on. What about the radon daughters collector? I mean, it's easy to find a sample of a radioactive material. I have here some examples, but how can I collect some radon daughters? So we need a second device, very easy. You can see on the right, this is a PVC tube with the fan at the end of a tube. It's a fan from PC, okay? And then I will cover the top of the tube with this fabric, this cloth. I have tried with different materials. This works very well. It is a filter that I use in the kitchen for the kitchen fumes. But there are, I think that any material that can, that is similar, I think that it will work very fine. So what we are going to do? We are going to turn on the fan, and the fan will put air inside the tube. Remember that the radion daughters, when are created, usually are ionized, meaning that are very sticky. So when a radion daughters is created inside the chamber, it sticks immediately with any material that is nearby. So for example, if I put air inside this tube against the filter, the fabric, many radion daughters will be collected on the fabric. Of course, I have to run this fan for about 1-2 hours. Just let the radon to flow in the fabric and accumulate many radion daughters. So I think 2 hours will be enough, but the important thing is that we decide an amount of time, for example, 2 hours, and we'll do many experiments in the same condition. So if I want to compare the radion gas presence in my room, in my school, and for example, in the basement, I can do the experiment. Of course, I can collect the radion daughters with the same parameters. So for example, I can run for 2 hours here in my lab this radion collector, and then measure with the ion chamber, and then go in the basement and for 2 hours collect radion daughters, and then measure the ionization chamber. So I think that we are ready to for sharing all this stuff, this amazing stuff. I hope you will enjoy. I'm asking Stefano, my friend and colleague, to help me. And okay, this is Okay. So this is our stuff. I have to see. Oh, wait. Come here, please. Okay.
Okay. Just to check, should I be spotlighting multiple cameras, or which one do you want shown?
No, this one is enough to check everything. So please, do you want to? Okay. So this is the ion chamber. Okay. So forgive me if you see some tape here, because I'm ready to open my ion chamber, but I will do it later, because now I want to check how it works and just to check if the measure of some radioactive particles. So the thing is, we have to read okay, here on the multimeter. It's great. Okay. We have to see also here together. So, oh, perfect. So, how it works? If I put something in front of a chamber, it will detect some radioactive particles. First of all, I switch on the ion chamber. You can see that in the first step, the ion chamber have to reach a stable condition of about less than 1 volt. Okay. And once it is ready, we can go on and measure some samples. I have here some samples of radioactive material, so please don't worry, it's not so dangerous. I'm warning my guest here because I have some radioactive particles. Okay, so first of all, the first sample I want to show you is from this. Okay, please, Stefano, let's have a look at this camping lantern. Okay, this is this is a gift when I was, I think, a birthday gift when I was a teenager. But anyway, this lantern works because here there is a gas mantle, this kind of web that is very bright when it burns, so it works very well. But in the 90s, it turned out that this gas mantle is radioactive. So I'm going to use it just to check if my ion chamber works. So this is a new sample of the web that of the gas mantle on the lantern. Let's have a look now at the multimeter. So the noise of this room is about 260 millivolt. Okay. Now I'm going to put here in front of the ion chamber a sample of the gas mantle. Let's do it, and let's see what that. You can see that the voltage immediately increased. We're talking about we started from 260. We are just over 300. That's amazing from a physics point of view, but if I think about how many times I changed this gas mantle on the lantern, it is not so amazing. Anyway, when I remove the gas mantle, the ion chamber will come back to the noise reading. So you can see clearly that is coming back to the previous value. And once they realized that the gas mantle was radioactive because of the thorium inside, they decided to produce this new gas mantle. And the thing is that if you look carefully, here there is a warning: no radioactivity, meaning that this kind of gas mantle is no radioactive. No radioactive. Okay, so let's check if it is true or not. Okay, so we are back to 250. Okay, let's put the gas mantle, the ecological gas mantle, and let's check. Yes, I can tell you that it is really safe because actually it's a different material, no thorium inside. So this really works. Anyway, I have here some patch blender. Remember Marie Curie and the study of the patch blender. So I'm going to take it to check how it works. This is a patch blender for didactic use. But anyway, I'm going to pick. Okay. Let's have a look. So, Michael, what do you think about this ion chamber?
I'm impressed. I like it a lot. Yeah.
So now we are going to collect some radon gas because, of course, it's clear that the ion chamber works. So the electronics is not that difficult, and it clearly works. And we are going to test the ion chamber with the radon detectors. That's the point. So first of all, I take the patch blender and put okay. We all are safe. Then now we are going in the basement of my school, okay? And I have put 2 hours ago there the radon collector. So please follow me for my microphone. Okay. Solo prima non vedo questo. So it's an opportunity to show you my school if you are interested. And we are going to the basement of my school and pick up the radon collector. Adesso sto condividendo. Can you see me now?
Yes, now we see you and you're full screen now. Perfect, thank you.
Okay, thanks. So this is my school. We are preparing for Christmas time. Okay, so you can see some decoration. Let's go.
That's why you painted the walls and doors green, and you have the other doors red in the red extinguishers to be in the Christmas theme.
Right. Okay. Perfect. That is the photo. Riesci a vedere ancora? I hope the signal is strong enough, but in a few minutes we will come back to the lab. Okay? Adesso porta a sinistra, attimo, accendi la luce sulla sinistra. Ottimo quest'anno il Radon Detector. Ok, illuminalo pure, questo è il Radon Collector. Ok. Perfetto, puoi tornare lì all'inizio. Fai vedere con basement, tutto pieno di concrete. Ok, voglio vedere lo stato. Perfetto. Ok, let's go. Oh, voi interesse tutto e finite tutto. Buonasera. Ok. Allora, esatto, il primo elementi la linux. Okay, we are ready to go. Just a few words about the Radon detector. The Radon Daughters detector, collector. Illumina, scusa, prima questo qua, che faccio vedere com'è. Grazie. So, how it works? This is a tube with a fan, and the fan let the air come inside the tube, and in this filter, many radon daughters are collected. So now I think that in 2 hours, this fabric is full enough of radon daughters. So let's put in front of the ionization chamber and check how the voltage is. Okay, perfect. I put here in front. Okay. Okay, you can see that is increasing. Of course, it takes just a few seconds to increase, but from 250, we are about 260, 65. $269. This increase of voltage is only due to the radon daughters on the cloth. So if it's a way to measure radon. But remember that if I leave here the cloth, as the radon daughters decays in some minutes, this voltage is going to decrease in a few minutes and come back to the basic level of noise. And this is one of experiments that I'm going to ask my student to carry out. The radon in itself takes 4 days to decay. The half-life time is 4 days. But the radon daughters are really minutes. And as in the fabric, there are many radon daughters, I think that in minutes, maybe 10 minutes, 20 minutes, we will find out through my student experiment, these radioactive particles will decay. Of course, the reading of this measure is not that easy because it is always floating. So we have to collect many data just to understand how the measure change in time. But anyway, it is clear that there is a difference between the basic level of radon and the level with the radon daughters nearby, very close to the ion chamber. Now I'm going to remove the ion chamber, the radon daughters, and in a few minutes the ion chamber will read the previous basic level. You can see that it is decreasing, and seems to me that it was about 250. Okay, great. So after all this presentation, I'm going to show you how the ion chamber is inside. First of all, this in front here, you can see just a shield. It's an aluminum foil, and I'm going to remove. I'm going to. Okay. And I'm going to remove just to let you see how I decided to prepare. You can see inside the wire. Okay. The position of the wire is not that critical, so you can leave in the middle, but there's no difference. It is not critical, the position. Then I'm going to open this side of the chamber. First of all, I remove the multimeter for the plug. Okay, let's have a look here. Sorry for the tape, but I usually seal all this stuff with some soldering or some special tape. Okay. Oh, here there is the magic. So I'm not giving you any further detail. I mean, you can see the battery here. I put a switch just to turn on and off the device easily. Here you can see 2 resistors. I hope 2 resistors. Okay, here. And here are the transistors. I'm going to show you all the details about this project available on the web. Of course, forgive me if you see all this tape, but I have to remove all the ceiling because this presentation, and once the presentation will be finished, I will put together all this stuff safely and in okay. And now I'm going to close. Just a look, just a brief look at the material. This is the can, okay, with a hole here. The battery 9 volt. And these are the transistors. I mean, 20 pieces, about €3 on the web. So I can give them for free to my students, don't worry. So it's very cheap. And that's all. So I can come back to the presentation. And I will show you the last few things about the possible activities. Thank you, Stefano, for helping me during this work in, okay, here. Okay, some ideas about, idea about the use of this ionization chamber. First of all, plot the meter reading versus time after the radioactive filter is placed against the ion chamber foil window. For example, we can take time, we can measure the multimeter every minute and go on for about an hour, for example. We are, I think that the typical decreasing graph, exponential graph of the decays will appear with this measure. So this is the first very easy activity that we can do with the ion chamber. Then we can compare the measurement in different rooms, for example, in other location, and old buildings, caves. As I told you before, the radion is mixed in air, but as it is much heavier than air, the radion flows down to the ground and accumulate in basement, in rooms with no ventilation. The third activity I would like to...
On Federico, just a tiny interruption. We've noticed that the video that we're seeing on is frozen. Should I switch the camera that I'm spotlighting to show Stefano's camera, or just leave your slides only without a video view?
Sorry, scusa, questi si può togliere il microfono adesso anche. Sorry, do you see the presentation now?
Yeah, we see the presentation. It's just we don't see you on the camera. That's shown like next to that.
Okay, yes. So, how well do various radon mitigation techniques work? Can a small fan make a big difference in a basement? Plot the radiation level before and after ventilating the room. That would be interesting because you know that the first way to remove gas radon from a room is to ventilate. And the last one is radon gas found in water. Does gas radon come out of a city water supply of other bodies of water? Because if you try and measure the radon in water, you can find an interesting level. So, of course, there are a lot of activities. But first of all of this project is not from myself, but is from a really smart guy called Charles Wendell. He's an electronic engineer. He lives in Austin, Texas. He's a businessman, and he runs an activity about electronics. And I'm in contact with him, and he's really smart. And what I really like the most that he do lots of experiments where you don't need to know so many things about electronics and stuff. And anyway, you can see all of the ion chamber project on his website. So let's check. This is the project. This is actually the tutorial that I used to prepare this ion chamber. So if you like to prepare yourself, just follow all this instruction. They are very detailed, and there are also some improvements that can be performed. And if you are really engaged in this project and you want something more, please have a look at all the science project in this website. Charles will be very happy. And also, I talked to Charles and told about this meeting, and he told me that all your colleagues can contact through email. You will not bother him because of your question. He is now retired, and he is eager to meet teachers and get in contact. So remember this website and the work from Charles Wendell. And I also put another link to some information about radon gas. Of course, there are many sources available on the web, but you can just check out these two ones. Anyway, if you are not satisfied with all these links, you can call me directly and ask me for more information. Thank you very much. So if you have any question, we have some minutes available for you to answer.
That's been really great. Thank you again, Federico. And there have been some compliments in the chat as well as some questions. Do you feel like going through what's been asked in the chat, or do you want me to pick through and relay them to you? Or?
Okay, let me check now. Question. Okay. What grade are your students in? Oh, you can have a look. Don't be shy. Oh, these are my students. They are of the last year of the secondary school in Italy. So meaning that you are 18 years old. Okay, they are able to drive a car. Okay, and they are preparing the ion chamber for the last for the final exam in the secondary school. Let's have a look at another question. Okay. What's the actual approximate cost to build it? A few euros. I mean, maybe if you don't have a multimeter, you have to buy one. Maybe some plug and some connection resistors. We have plenty of this material here at school, but if you want to buy online, I think that 10 euros, 20 euros will be more than enough, surely. Of course, you have to prepare carefully. You have to spend time to prepare and to check that everything is okay. But this is why I have my student preparing the experiment. And of course, remember that you will leave your device here at school once you will go to the university, okay? And I want to build it immediately. Yes, the transistors are easy to get, yes, of course. Amazon, of course, but also eBay. If you have time, some Chinese supplier, just like AliExpress, you don't have them. There is no problem, are really available. This kind of transistors is called Darlington because actually are two transistors connected together, okay? And you can find in the tutorial the exact definition of the code of a transistor. It is a BC433. I mean, anyway, you can easily find on the internet supplier. And will a high voltage battery increase the measurement sensitivity? I don't think so, because I wanted to increase the measure of the voltage, so I put two Darlington transistors in cascade, one after the other, okay, to amplify more, but there is a limit, okay. I don't know how it works with high voltage, but I know that interference from outside may be more critical. This is, I think, a very balanced project. And information transistor. And okay. I see that clear. Can we use it to prove the first law? I think the first Ohm's law. Yes, of course. I mean, you can use this circuit to understand how the current flows, and of course the first Ohm's law. But when you use a transistor, things go slightly different, because the transistor inside require some voltage. So you need to check carefully all these values just to apply the Ohm laws to the circuit. But maybe I've never done it. The gift for the school, I know. Okay, to message. About water, so Charles Wenzel carried out many experiments with this ion chamber. The radium gas is one of them, but there are also other experiments. For example, with second-hand smoke, because the ionization chamber can read how the smoke affects the radon collector. Because you know that if there are particles in the air, the radon daughters will be ready to stick on this particle. And that's the problem. So you can find in the presentation of Charles on his website some experiment about that, and with some analysis from a scientific point of view. That's very interesting. Radon gas is also in water, because you know water is in the soil, so it's everywhere. And the concentration of radon into water is quite significant. So you can do with tap water. Of course, you have to leave the radon collector for some hours nearby, very close to a tank, some waters, and do the experiment. On the website from Charles, there are also experiments about gas radon on water. And then, is there any can do this? Make a graph part. Yes, we are talking about quantitative measurement. I told you during the webinar that we are talking about thousands of electrons that per second that are free to move in the ion chamber. In the description of Charles on his website, you can find some calculus about that, because he applies the first Ohm's law, okay, to measure the current. So voltage over resistance, you have the current. And he found out that we are talking about femtoampere, meaning about 102,060 electrons per second. Here you can find some specific measurement. Of course, you can do it only if you know exactly how much the transistor amplify your current. That could be very tricky, so I'm not asking students to do that stuff because it's not our goal. But if you want, you can go and dive in that section of electronics, and maybe you will find some result very significant. Okay, I think that if I bury the detector several feet in the ground, could I expect higher levels? Yes, I think so. I think so. It could be interesting to bury the detector in the ground. Why not? I never done it, but this is an idea, and remember that you can do the same. Okay, just bear, I don't know, 1 meter under the ground and measure. Why not? Thank you for the idea, because it's great. Okay, I think that we are ready to prepare our ionization chamber. Please feel free to contact me if you need further information. I think that it's a cool experiment, and of course, I'm asking only 2 students of mine to prepare it carefully, and I will follow all their activity, and then we will show to the class, to the other students, all the experience. So, Michael, if you want to ask me something.
Yeah, I was on mute and didn't realize I was on mute when I started talking. So I started to thank you again. So it's been really great to have you taking us through all this. And I hope everyone makes their own detector. Those of you who do, please try and take a photo to send to me and to Federico, because it's always a great pleasure when we see ideas living on like this. And as Federico and I were talking about just before the session, I hoped, and I hope everyone agrees, this was a perfect transition from Jesus's session on Tuesday, for those of you who joined for that, going through the scientific point of view of the history of gas detectors to something that you can actually do in a classroom. And that, like, this week has been, in a lot of ways, my favorite week of what I've been trying to accomplish with this course, bringing in expert teachers to help share ideas that you can do in the class, and expert scientists showing the cutting edge science behind that. So I've been really thrilled for this.
That's great. And remember that if some students of yours would like to prepare the experiment, they can share their results with my students, so we can compare also the radon activity, not only in Italy, but compare it with, I don't know, France, England, Guatemala. I saw many countries connected. Why not? We can compare all this radon activity in different countries. Why not? So feel free to contact me, and I will let my student get in contact with yours.
Oh, that's a great idea. Yeah. And then just as we're finishing up, to remind everyone for next week, there's been a small schedule change. So the order of the team from CERN Science Gateway and Claire David in Ames, South Africa, is switched around. So Science Gateway's resources and their new educational portal will now be on Monday at 6 o'clock Central European time, like Paris, Geneva, Brescia. And Tuesday will be Claire David with the triumphant discovery of the Higgs boson, again at 6 o'clock Central European time. So it's been a bit of a switch. And I realized when I was looking up to remind everyone, somehow when I went to update the website, I didn't actually save the update. So the website is wrong. I'll change it as soon as we get off the call. But Monday and Tuesday, sorry, they're 2 days in a row. It was the people joining, the constraints for that. I would have avoided it if I could, but sorry about that. So with that, I'll thank Federico one last time. Thank you again, and thank you everyone for joining us.
Thank you. Bye-bye from Italy.